Welcome back, ladies and gentlemen. Here we go, talking about electric circuits, or at least introducing the idea of an electric circuit. So we have a basic definition here. Any kind of pathway that electric charges can flow through, and usually we're going to make a closed loop out of that pathway. Well, regarding circuits, you want to understand a couple things that all electric circuits have. So they include the following. There's a thing that sometimes will be called a charge pump. And you might actually literally think of it as a pump. It pumps the charges. Well, when a pump is working on water, it actually is physically correct to talk about working on water. It does work on the water, so it adds energy to the water. Well, a charge pump adds energy to charges in a conductor. So you want to make sure you understand that. It's something that increases the potential energy of charges flowing through it. So what could this be like? Well, a charge pump could be like a battery. As charges flow through the battery, they're going to pick up more energy, and they act as little delivery vehicles. They're going to deliver that energy somewhere else. I'm also going to use a term quite often, and I'll use it very generally. It's just a resistor. Now, to somebody who maybe designs electric circuits or repairs them or anything like that, a resistor means something very specific to them. For our purposes, a resistor is simply something that reduces the potential energy of charges that flow through it. So it's just the opposite of the charge pump, essentially, where a charge pump increases the potential energy of charges. A resistor reduces the potential energy of charges flowing through it. And that's kind of it. That's the out and the in of a circuit. The charge pump increases the energy of charges, and the resistor reduces or decreases the energy of the charges. Notice neither one of these makes charges or destroys charges. That's not the idea. That's not what's going on inside a circuit. Kind of like when water pumps water from one location to another, the water isn't created or destroyed, it's just made to move. That's it. Now, the potential energy lost by the charges moving through a resistor. So a little kind of extra bit here about a resistor. The potential energy lost in the resistor is usually converted into other stuff, useful stuff. You might have a device that makes motion, get something to move, like an electric motor. You might have a light bulb that makes some light for you. You might have a little speaker making sound. You might simply want some heat out of it. So energy is conserved. The energy that's taken out of the circuit isn't just destroyed and lost. It's converted to other stuff. I wrote the word motor. I meant to write the word motion. T-I-O-N. Motion. When you plug a motor in, you get motion. You get the idea. You know exactly what I'm talking about. Now, what about the charges then? Well, since what's really being used is energy, the charges are simply delivering the energy. So this is real important to understand. the charges themselves are not used up. Or destroyed. That's real important. Charge is conserved. You have the same number of charges before and after. Maybe you turn on the circuit and then turn off the circuit. You got the same number of charges in there. It's just whether they're moving and whether they have a lot of energy that they're carrying or not. Super important. Charge is conserved. Now, the potential energy is used up and it must be replenished. And so that's why you have a charge pump, to replenish that energy that is used by your circuit. Okay. Get the sense that we're going through a bunch of ideas and some definitions. Well, that'd be a very fair assessment of this video. So now I want to get to some nitty-gritty stuff. The charge pump itself, it creates what's called a potential difference. We generally don't say potential energy difference. We just say potential difference for electric circuits. Now, potential difference is also known as voltage. This is what the charge pump creates for the circuit. Now, potential difference, technically speaking, is the amount of energy per charge. Cool. And that's easy to understand. And now energy is measured in joules, right? Joules. And charge is measured in coulombs, capital C. And the nice thing is that we can combine these two, joules per coulomb. We usually don't say that. We usually instead just talk about volts. Capital V for volts. Now the silly thing is, you also have a capital V for the symbol for voltage. It's just the way it is. Okay, so V for volts or voltage. Also, I'd like you to recall that current, current, what does that represent? That's an amount of charge divided by time. So how much charge flows in a certain amount of time. And so this is real cool. Watch what we're going to be able to do. We're going to be able to take this expression for current in an electric circuit. We're going to say charge per unit time. And we're going to take this expression for voltage, energy per charge. And we're going to multiply and watch what happens. So we put it right next to each other. Energy per charge. Right? We're just going to multiply and see what's going on here. This came from here. This came from here. And now you already see what's about to happen, don't you? Look at this. Charge cancels when you do that multiplication. And what you get when you multiply the charge per time, which is current, times the energy per charge, which is voltage, you get energy per unit time. So essentially, this is how much energy the circuit is using per time, right? It's the rate of energy usage. Well, there's another name for that, and that is electric power. Cool. And the symbol for power is just a capital P. That's very straightforward. The units for power are watts. Now, I think we've seen this before. The abbreviation for watts is a capital W. Okay, so there's the units, watts, capital W. What I'm going to do for you is break this down a little bit, because all these new symbols can get a little confusing. Let's take a look. So we're going to have the name of the quantity. We're going to have the symbol of the quantity. We're going to have the units of that quantity. So we'll do it like this. Make a little chart so this is a little easier to remember. One of the things we have to learn about is current. This is one of the first things we looked at. Oh, you know what? Even before current, we looked at electric charge, didn't we? So let me do that. Let me throw charge in here. Electric charge. Electric charge. Well, the symbol for charge, we're using a lowercase q. The units of charge are the coulomb, which is a capital C. Okay, so you see how this is working out. We also learned about what? A current. Okay. Electric current. That's an E. Well, the electric current symbol is a capital I. The units of current are the ampere, sometimes called amp for short, and the abbreviation is the capital A. Well, what kind of new things have we seen just recently? We have seen voltage. Okay, so let's throw that on the list. Voltage, symbol is a capital V. And the units are volts, and the abbreviation is a capital V. That's a little strange right there, but okay, go with it. Not hard to deal with, right? Now we've also seen electric power. Okay. Capital P is the symbol for that quantity. The units are watts. Capital W. Now, there's a couple things to keep in mind. I'm going to switch colors here. This is a very handy chart to memorize, because you need to have these terms and symbols well understood. You need to know what you're talking about. For example, how might you get screwed up? Well, you might see a capital W and think, oh, well, I know what that is. That's work. Because I remember seeing work and the work energy theorem and all that, the good stuff, right? And you think, yay, I got it. But maybe that capital W is the units of electric power, watts. Here's how you tell the difference with this one in particular. If you see a number in front of the W, let's say you've got 100 capital W, then that makes this the unit, not the symbol, right? If you see no number and an equal sign, so it's just the capital W all by itself, and an equal sign, and then maybe some other stuff. Oh, maybe it also, you see force times distance, because that's equal to work. Then that would be, the W by itself would be the symbol of work and not the unit of power. Cool. Okay. V. Well, don't get confused with a capital V for volts or voltage and a lowercase v for velocity. That's another thing you might accidentally get mixed up. Cool. Now, from this, right, I'm going to come back to this now. From this dealie right here, current times voltage gets you power. Let me rewrite that for you. We have power equals current times voltage. This right here is one of the very important equations for electric circuits. It's the equation for the power in a circuit. And it's easy. It's a very simple equation. Cool. And so now remember what power is. Power is the rate at which energy is transferred or used. So the rate of energy transfer. So the energy per time. Cool. Let's look at an example of this, just because it's going to help it sink in, help us remember. if we have a 1.5 volt battery that is creating a 1.33 amp current in a circuit. I'm going to want to know how much power is used by the circuit. Sometimes the wording is different, how much power is used by this circuit. Sometimes the wording will sound like this: how much power is dissipated by the circuit, or how much power is consumed by the circuit. That kind of all mean the same thing, at least for our purposes here. So here's what I've got to do. I know the equation for power. Very straightforward. Current times voltage. So I know the current is 1.33 amps. And I know the voltage is 1.5 volts. And when I do this math, I get a power of 2 watts. See, the capital W is coming after a number. So if it comes after a number, then I know that is a unit. There's my answer to the question. 2 watts of power. Okay, now what if, or how would the power be different if the battery supplied 6 volts instead? Just letting this sink in. How would the power be different if the battery supplied 6 volts? Question. Well, okay. I simply go back and say, power is going to be current times voltage, but we are increasing the voltage from 1.5 to 6 volts. So I've got current times voltage. Got the current is the same, 1.33 amps. Now the voltage, going from 1.5 to 6 volts. Okay, I could write a 6 here, and that's easy enough. And when I do this math, what I get is 8 watts. But let's look at that 6. We can break this down another way. I can say, well, instead of the 6, we have the 1.33 amps. That's my current. And the 6 is going to be a 1.5 times what? It's going to be 4 times 1.5 volts. So essentially, I've multiplied by 4. Another way to look at this is the 8 watts is equal to 4 times the original answer of 2 watts. So right away I can see the real answer to the question. How would the power be different? Come on, paper's moving a little bit. The power is, how would you describe this? It's 4 times larger, 4 times greater. Boom. And that's our answer. That is the answer to this question. Awesome. Now, there's one more piece of this kind of puzzle, so to speak, that we need to look at. And this piece is the resistors. Final piece are resistors. Now, again, I do use this term rather loosely. Resistors have sort of 2 very broad general purposes. Sometimes a resistor is simply used to slow current down. They do that. They slow current, or they reduce current. I happen to have this device open, And you can see a bunch of stuff going on in here on this circuit board. And some of these components are resistors, and all they do, all a resistor is meant to do, is actually reduce the current in part of that complex circuit. That is their only function. And so when you hear the word resistors and you're thinking of those little tiny parts inside a circuit, they are just there to control or to slow the current down. But also, some devices that I call resistors are those things that are doing something for you. They're useful. They produce the motion, the light, the sound, or the heat, right? Okay, now, what about resistance of a part of a circuit? Well, it kind of depends on several things. Number one, it depends on what it's made of, the type of material. Some materials are much better conductors and they will have a low resistance. Some materials are poor conductors or good insulators, and they'll have a relatively high resistance. If you have a wire, let's say, the resistance in the wire does depend on the length of the wire. A longer wire will have more resistance. It also depends on the size or thickness of the wire, the cross-sectional area of the wire. And it's kind of like a pipe. Well, a larger diameter pipe can carry more water. A larger diameter or larger size conductor with a larger cross-sectional area will have lower resistance to the charges moving through it. One final thing is temperature. And you've heard of superconductors. Well, what they have to do for superconductors is cool them way down, and they see the resistance of those materials decrease and sometimes even go to just about zero resistance, almost zero. I'm not quite sure if they've actually achieved truly zero resistance yet. That'd be worth looking into. Kind of interesting. Now, how do we measure resistance? What you do is you measure the resistance of something by placing a voltage across it. It's kind of like plugging a battery in to some oh, that's not the one I need to show you. Oh, well, sure. You have to have a charge pump. You have to have something that gives the charges in that material some extra energy. Excuse me. So what you do is you provide that voltage, and let's say you want to test the resistance of this guy right here, whatever it is, and you apply that voltage to it, and you'll get a certain amount of current flowing through this object. The amount of current really tells you the resistance. So how does it do that? So measuring resistance. Oh, by the way, capital R for resistance is the symbol we're going to use. Aha! I need to add that to my chart. Electric resistance. So you want to go back. That's a capital R. And the units. This is going to be kind of a strange one. The units are ohms. And of course, everyone jokes around and says ohm. Right? It's a little silly. The abbreviation of this unit is not an O. It's a Greek symbol omega, capital omega. So we're adding yet more new terminology that you want to be familiar with. Okay. Now, when you measure resistance, what you do is you essentially measure the voltage you're applying and the current that it produces, and the resistance you get is the voltage divided by the current that you see. So this right here is also known as Ohm's Law, named after from you know, I think a couple centuries back. I forget his first name. George, possibly. I think it might have been George. He did some work with radio and radio signals, but he basically did the first initial work into discovering that for a given material, if you increase the voltage, then you get more current out of it. So Ohm's law is essentially usually written this way. The voltage is equal to the current times the resistance, and that's just rearranging this relationship right here. Now there's something cool that I like to do. I actually prefer to see this, just for my own understanding, written as the current is equal to voltage divided by resistance. Here's why I like that, but let me show you. Let me put a box around Ohm's Law. It is huge. This is a very important idea. Very important. Memorize that. Super duper good. The reason I like to write it like this is because it shows that the current that you get in flowing through a circuit, is directly proportional to voltage. So current is directly proportional to voltage. It also shows that current is inversely proportional to resistance. And one more thing here, when you write it like this, it is essentially showing dependence, that current is a result of a certain voltage and a certain resistance. It's not the other way around. You don't have a certain resistance based on the current flowing through it. It's the voltage you apply and the resistance of whatever it is that determine how much current flows through the circuit. So I like to look at it this way, but Ohm's Law, you can look at it this way or this way. In fact, let me show you something kind of cool. Watch this. This works for just about any equation where there are those three components. So let me rewrite Ohm's Law here. Typically V equals IR, but you can also write, the way I like to do it, I equals V over R, or you can also write R equals V over I. Okay. Any one of these is Ohm's Law. Watch this. Which one do you need? If you have, you can essentially make a triangle if you like. This is one way of doing it. And in the triangle, you draw a T. So check this out. What I'm going to do is I'll take this original form and I'll look at it and say, well, if I multiply current and resistance, I'll get voltage. So here I have two spaces next to each other, and when numbers are next to each other, that typically means multiply. So I'll put those there. I just screwed up, so that's supposed to be R. Sorry. And now, so I put voltage here. And this deal right here, watch this. Using Ohm's Law, if I want to find the resistance, I cover up the resistance. And what I have to do, this tells me I have to divide voltage by current. If I want resistance, I divide voltage by current. So if this gets you kind of confusing, you can just remember one triangle. Just memorize this, and it'll tell you. If you want to find the current flowing through a circuit, cover it up. It's voltage divided by resistance. That guy. If you want to find the voltage, cover it up, and it is current times resistance. That guy. Anyway, that might be a little handy for some of you people who are so inclined to use that kind of thing. That's cool. One final note. The resistance of a component in a circuit is usually constant. But the circuit can be designed with any resistance that you need. So what this means is that for a given resistance, more voltage produces a larger current. I'm writing extra bold here too, a given, and you're writing this down as well. You're taking notes, right? For a given resistance, more voltage that's an E, produces a larger current. End statement. This is a very important thing to understand. It's just like in our analogy with the waterfall, and if you have a stronger pump, then what's going to happen is it's going to force more water to